ladies and gentlemen of the pre-calc. Today, it is our chance to look at how we can apply these rational functions to the real world. I'm going to work through one example with you. This example is going to be about one of your and my favorite subjects, chemistry. So imagine you got a beaker. Do you have a beaker? I got a beaker. It's right here. Imagine that you've got a beaker and you're performing an experiment, and you filled the beaker with 150 milliliters of water and 50 milliliters of pure acid. Let's go through some questions together. A says, show that the acid concentration of the substance is 25%. And this is a good place to remind ourselves that a concentration is a fraction, which is perfect because fractions are what we've been talking about in this unit about rational functions. So for this fraction, we would say that the total amount of water, actually I shouldn't say water, the total liquid is your denominator. The total acid is your numerator. And to start, we have 50 milliliters of pure acid. So I'm going to put a 50 in the numerator. And our total liquid would be 50 milliliters of acid plus 150 milliliters of water. So that's 50 divided by 200, which simplifies to 0.25. Multiply that by 100, and we get our 25%. So imagine that your beaker here, it's got 200 milliliters of solution in it. It's a 25% acid solution. Now we're going to start looking at what happens to the concentration as we add more acid to the solution. So here we go. Take a look at B. B says, what would be the new concentration if you added 10 milliliters of pure acid? So if we added 10, I want you to think of it this way. We've already got 50 milliliters of pure acid. We've already got 200 milliliters of liquid. If we add 10 milliliters of pure acid, we've got 10 more in the numerator. We've got 10 more in the denominator. This turns into 60 out of 210. Grab my calculator. Okay, so now we've raised the concentration to, I'm going to call that 28.6%. Okay, this says, what about 20 milliliters? Well, if we added 20 milliliters, this didn't change. And this didn't change either. The only thing that changes is instead of a 10 and a 10, we've got a 20 and a 20. So I'm trying to make the point to you that as we add pure acid, this value and this value, right there and right there, are varying. So let's see, that would give us 70 over 220. That raises our concentration up to 31.8%. Okay, so here's some things that shouldn't surprise us. As we're adding more pure acid, we can watch our concentration going up. Now, things are going to get a little more interesting. Take a look at C. C says there's currently 50 milliliters in. All right, so we're back to this situation. If you add 50 more milliliters, so if you double the amount of acid, will that double the concentration as well? So if we double the amount of acid, does that also double the concentration to 50%? Let's see. So once again, we're in the same situation where we're starting here, but this time rather than adding 10 or 20, let's add 50 on. That would give us 100 over 250, which is not 50%, is it? In fact, if you do that, let's see, that's 10 over 25. 10 over 25 is 40%. So the first thing we should take away here is that just doubling the amount of acid isn't necessarily going to double your concentration. Our goal is to figure out how much acid would double the concentration. In order to do that, let's look at question D, which kind of sets us up for this. It says, I want you to write a function. We're going to call it C of x. C of x is going to be the concentration when we add x milliliters of the pure acid. And I hope that I've set you up here where you can figure out what C of x is going to look like. Because listen, when we wanted 10, we put a 10 here and a 10 here. When we added 20, we put a 20 here and a 20 here. When we added 50, we put a 50 here and a 50 here. So if we wanted to add x many, what would our concentration equation look like? Well, we would just take those spaces. We would replace them with x and x. So your numerator is x plus 50. Your denominator is x plus 200. So this is kind of cool. We've now got the ability to model what happens to the acidity of our beaker as we play around with the number of milliliters of acid. Let's do this. Take a look at E. E says if we want to know how many milliliters of acid to pour into the beaker in order to get to 50% concentration, we could solve the equation, make the concentration equal to 50%, 0.5. So 0.5 is equal to x plus 50 over x plus 200. There's lots of different ways to solve an equation like this. I personally, since it's already a proportion, would think about cross multiplying. So if we cross multiplied, we would end up with 0.5 multiplies x plus 200 is equal to 1 times x plus 50. So 0.5 x's, distribute that 0.5 to the 200, we get a 100 equals x plus 50. Subtract a 0.5x from both sides of the equation. Subtract a 50 from both sides of the equation. These cancel. These cancel. We're left with 50 milliliters is equal to half of the number of milliliters we need. If we divide by 0.5 on both sides, we get that x should be equal to 50 divided by 0.5 is 100 milliliters. Okay, cool. All right. Next thing. F asks us to state the asymptotes of this function. I think it might be easier if I just write this work up here. So we're looking at the concentration equation. First, it's going to have a vertical asymptote. Anywhere that the denominator is 0. So when x plus 200 is equal to 0. And that would occur at x is equal to negative 200. Now, this is not a super meaningful asymptote for us because there's no way that we could ever put negative 200 milliliters of acid into the beaker. The end behavior asymptote, on the other hand, this one's a little more interesting. Notice that x is our variable, and the degree is the same on x here and here. So we know that in that situation, we want to look at our leading coefficients, which are 1 and 1. So we would conclude that our end behavior asymptote is equal to y equals 1. And that is going to be meaningful when we look at the next part of the problem. So let's move forward. G says to construct a graph of C of x, only graph for positive values of x. Be sure to label your axes. Show the end behavior asymptote as well as the y-intercept. Okay, so here we go. G. Let's call this x, which is our number of milliliters. And this would be C of x, which is our concentration. And we know there's going to be a y-intercept. That y-intercept, put right here. Oh, sorry, did I say y-intercept? I misspoke. I meant a y-asymptote, an end behavior asymptote. And that's going to be at y is equal to 1. And we know that when we plug 0 in right here, 0 milliliters, we get 25%. So I'm going to start right here at, we know this goes through 0, comma 0.25. And we also know that the concentration keeps going up and up and up and up as x increases. So it's going to look kind of like this. It's going to go up, but it's going to level off, and it's never quite going to hit that end behavior asymptote. Which brings us to the last question, to H. H says, how many milliliters of acid must you add to raise the concentration of the substance to 100%? Explain your answer using your graph. Well, let's keep in mind that y equals 1 is equivalent to a concentration of 100%. So our answer is going to be, how much x do we have to add to get up to a concentration of 100%? There is no amount. Okay, we will never reach a concentration of 100%. Now, some of us would say, this is sort of a no-duh situation because there was already some water in there to start, and that water is always going to be there, and it's going to prevent us from ever hitting 100%. But we can also see it here graphically because C of x will never touch the asymptote. All right. So we've gone all the way through number 1. What I would like you to now complete is to do number 2 and to do number 3. And then I want you to stop right there because the rest of the problems are optimization, and we'll talk about that next time.